Welcome to the first video in section 4.1 on local extrema and the second derivatives test. The goal of this section is to be able to locate local extrema and saddle points of a function of two variables and classify them using the second derivatives test. Definition 4.1.1. Let f be a function of two variables. F has a local minimum at AB if f of xy is greater than or equal to f of AB for all points xy within some disk around AB. F has a local maximum at AB if f of xy is less than or equal to f of AB for all points xy within some disk around AB. And if the inequalities above are valid also for all xy in the domain of f, not just around some disk, then f has an absolute or global minimum or an absolute and global maximum at AB, respectively. Let's review the situation about local extrema for functions of one variable. To find local extrema for a function f, in your first calculus course you looked at places where f prime of x equaled 0 and f prime of x did not exist, because you had the following shapes of function graphs in mind. Places like these where the derivative was horizontal. If the derivative is horizontal, f prime, if we call this point A, f prime at A is equal to 0. But there were also places with sharp points like this, again if we call this A, where f prime of A did not exist. For functions of two variables, there are some corresponding shapes. We've seen them already. So paraboloids are a good example, although this kind of shape can exist on other function graphs as well. And of course, it's not the tangent line, which is horizontal in these kinds of cases, but the tangent plane. And if the tangent plane, again, if we have a point, let's call that point AB. If the tangent plane is horizontal, it's because the partials are both 0, and if the partials are both 0, the gradient of f at AB is 0. We've also seen some examples of sharp points. Half of the double cone, for example, we've seen this. Clearly here we have a minimum, a local minimum, and a local maximum, but the function was not differentiable, so the gradient at that place does not exist. But that's not the full story. Not all places in Calculus 1 where you had a horizontal tangent line or where the derivative did not exist, not all places gave local extrema. You had already also seen the following kinds of graphs. A point like this, where the tangent line is horizontal. So again, if we call this A, f prime at A is 0, yet there is no local extremum. Also like this, vertical tangent lines. Somewhere like this, f prime of A did not exist, and yet there are no local extrema. Again, we have corresponding pictures for functions of two variables. We've seen both of these examples before as well. The hyperbolic paraboloid has a lovely flat spot right there where the tangent plane would be horizontal. The gradient at that point would therefore be 0. We also saw this example in a previous video where the function f is not differentiable at, as it turns out, the origin, And yet, in both of these cases, we have no local extrema. So like you did in Calculus 1, you had to figure out how to distinguish between cases where the derivative was 0 or did not exist that led to local extrema and those that didn't. We will do that in another video. First, let's define a saddle point in definition 4.1.2. So a point AB is called a saddle point for a function f if the gradient is 0 there, but f does not have a local extremum. For example, here, this is the quintessential picture that people have in mind. We described this shape even as a saddle when we were first describing our quadric surfaces. A saddle point, that point which is a minimum in one direction and a maximum sort of in another. That is the classic picture of a saddle point. In the next video, we're going to see definitions and theorems relating to functions of two variables that'll help us figure out when we have local extrema and when we do not.